In the last video, we looked at these two types and we instantiated functor instances for them. So both of these can now be mapped over. However, both of these are good candidates for the foldable type class. So again, foldable lets us get away from just working with lists to working with more complex data structures, like our binary tree here. But we'll start by instantiating foldr for this one, the list here, and then we'll have a look at instantiating a possible version of foldr for a binary tree. So let's have a look at the foldable type class first. If I could type, there we go. So now the minimal is either foldmap or foldr. We haven't had a look at foldmap, so we should be trying to instantiate foldr here. And you can see that there's a bunch of stuff here, there's a lot of complicated stuff. But foldable type is essentially something that can be reduced down. It can be reduced down into some sort of characteristic value for it. That's what foldr does. So if we have a quick look at the type of foldr, we'll remember that, well, this has got loads of foldr, so let's get this, yeah, there we go. So we need something from A to B to B, and B, and then a T of A and B. So in this case, this T here will be this list, and then it will be this B tree here. So that's allowing us a bit more flexibility in how we define things. So let's have a look at instantiating. What, did I spell that wrong? I think I might have. Is it foldable? Yep. And list. Where? And now we have to decide how to define foldr. Now I'm going to say that foldr for a function, for an accumulator, and for empty should return the accumulator. That's what we said with foldr. The accumulator is something that replaces the empty list when you get down to the final case of the recursion. So in that case, we should just return the accumulator. Now we have to do a little bit more work when we have f, ac, and we have something of the lines of cons a and x's. Actually, we should call that x if we're going to call that one x's. So what do we do here? Well, we know that this is the recursion scheme that takes f, applies it to x, and then to the recursive call. So what we should have here is f of x, and then we should call foldr with f, ac, and x's. So this is how we recursively call through the list, calling the values, applying f of x to each value as we go, and then eventually we get down to the base case, which is when we have the empty, and we replace that with an accumulator, and it will apply f to that and the final value in the list. And that's how we do it for that one. And you could think of this as quite clearly we've just replaced f, cons here with f, and then recursively worked on the x's. Now, it's a little bit trickier for the tree. The tree is a little bit of a more difficult class to work with. But let's see if we can manage some sort of definition here. And we want foldr, not foldr, foldr. Now again, this is going to have an f, it's going to have an accumulator, and this time it's going to have a leaf. And again, you'll notice these base cases are the same, so we just replace this with the accumulator, and that allows us to move down to or replace the final values with a value and then come back up. So then, when we have something more complicated, we have f, we have ac, we have node, left tree, we have an x, and we have a right tree. So what do we do here? Well, the definition I'm going to go for, I'm sure there are more than one ways to define a fold on a tree, but I'm going to say that foldr should still have f, but its accumulator should be replaced in this instance. So what I'm going to say is, what we do is we recurse over the left tree, and then once all of that is finished evaluating, we come back and then we do the right tree. So I'm going to say that the right tree is what happens next. So in here, I'm going to have f, and I'm going to have x, and I'm going to repeat the pattern that we saw earlier where I have foldr, I have x, I have accumulator, and I have the left tree here. So you'll see here, this is the same sort of recursion pattern that we had up here. It's just being applied to one tree at a time, and then once this is finished evaluating, we'll have the fold value for the length of the list. Well, that should be, yep, I understand Haskell, there we go. So what this will do is it will work its way down one of the sides of the tree, the left tree first, and it will replace the accumulator with the folded values, or the fold value from the left tree. And then when it comes back up and it's finished evaluating, we have a new accumulator with which to repeat our recursion scheme with the right tree. So this is one way you could think about defining this. There will certainly be other ways. This isn't the canonical way. There's other ways to define fold functions on trees. You might say this is more of a left fold than the right fold. I'm just going to use this as one instantiation of how we could do this. But you can see these form a similar structure. So now, if I save this and I reload, then I can say fold R, and let's just say I want to add up the values in a tree using 0. And let's say we have node, so we should put brackets around this. So we have a node, we have a leaf, with the value of 5, and then we have another node which has 2 leaves and a number 5. So here we should get 10 out. We hit enter, and we do indeed get what we expect. So this is one way where you can instantiate these foldable instances, and you can see actually they're not too bad to instantiate. They're not too much code. It's just getting into your head how you should recurse through the structures that you're working on. As I say, there are other definitions here that might be more suitable. We might have a look at some of them later on in some other class or some other exercises. But for the moment, I just want you to take in that a functor is something that can be mapped over. A foldable type is something that can be reduced. Okay, that's everything for today. I hope you found this useful. Of course, if you have any questions about this, please do let me know. Thanks.